So hello my dear students, today we will see some more examples on eigenvalues and eigenvectors. The question is from practical number 3, second example. Yesterday we have seen first example from practical number 3 and we have seen two sub questions from that. So it is your homework to solve the rest of the questions. So now we have to find eigenvalues and basis of the corresponding eigenspaces. Now why it is said basis and why not basis? Because they are using plural eigenspaces they are saying. So the plural of basis is basis. So we have to find basis of each eigenspace actually. Matrix is given. And now the next question is interesting. Hence we have to find eigenvalues and basis of the corresponding eigenspaces of this following matrices. A inverse, this one and this one. So first of all we'll go for this matrix, then we will go and see what will be the eigenvalues and eigenvectors for this matrices over here. So the characteristic equation of A is given in this way. So you will get some such kind of matrix will be equal to 0, and after solving so this you already know, and we'll get the eigenvalues to be 1 2 3. So 1 2 3 will be the eigenvalues. Now we'll go for the eigenvectors. So I will say we have this as eigenspace corresponding to eigenvalue lambda. So I have taken a vector from this E of lambda. Why it is a vector from R3? Because we are dealing with 3 by 3 matrix, and we'll get this kind of equation because that is what we are having, right, in E of lambda. Now so how to get this matrix? See, this matrix over here lambda I minus a is exactly same as this determinant. So you don't want to do something extra, just you have to copy this as it is. Only the difference is over here you are having determinant and over there you are having a matrix. Okay, I'm calling it a star. Now we will find eigenvector corresponding to each eigenvalue. So for lambda is equal to 1, what we will do is I will put lambda is equal to 1 in star. Now as told yesterday, since all the eigenvalues are distinct, so therefore we can use Cramer's rule for each eigenvalue. So 1, 2 and 3, isn't it? None of the eigenvalue is repeated. It means the multiplicity of each eigenvalue is 1. Okay. What do you mean by multiplicity? If the root appears twice, isn't it, to some polynomial. Now in this case the multiplicity of this root is going to be 2 and multiplicity of the root 2 will be 1. Okay, so whenever you are having all the roots having multiplicity 1, then you can go for Cramer's rule as I have told you before. Okay, so if you put lambda is equal to 1 in star, so what you are going to get, you will get this matrix. So it will be 3 minus 2 minus 3 2 minus 2, this will be minus 2, this will be 4, this will be minus 2 and this will be minus 4, and outside you are going to have x, y, z. Now we are going to use Cramer's rule for this, but for that purpose I have told you we should look for the linearly independent rows. Okay, so what I see is from the observation, you can see that if I multiply this second row by 2, then you're whether you're getting the third row, I don't think so. Okay, so either you can use first row second row or second row third row, and I think you can use first row and third row also. Okay, but in this case I will go for first row and second row because that seems to be natural. Yes, so I'll say by Cramer's rule. X upon determinant of, so you leave this I'm using Cramer's rule for first and second row, that is you are supposed to understand. First of all, since I am finding the variable x, now leave this coefficients of x and you are directly going to take determinant of what, this minus 2 minus 3 minus 2 and minus 2, which will be further equal to minus y, don't forget this minus sign, determinant of, now we are going to forget about this coefficients of y, so I will write here determinant of 3 minus 3 2 and what, minus 2, which is equal to z upon determinant of, now I am going to cut out these coefficients of z, and what is left out, 3 minus 2 2 and minus 2, which is equal to some t. Now let us simplify it. You just check the calculations, huh? Okay, so therefore what I am going to get, therefore x upon So 4 I will get, right? So 4 minus 6, I guess. So 4 minus 6 is going to be minus 2 over here, which is further equal to minus y upon, so it will be minus 6 plus 6, that is going to be 0. So over here you will have 0, which is equal to z upon, you will have minus 6 and I guess plus 4. So minus 6 plus 4 is going to be minus 2 again. So minus 2 will be equal to t. Therefore, my value of x will be minus 2t, value of y will be 0, and value of z will be minus 2t, where this t is a parameter. Okay. So therefore, you got the eigenspace over here. So what is your eigenspace? Therefore, see, I got the value of x and y, x and z to be non-zero. This should happen. At least one coordinate should be non-zero. If all of them are zero, it means you have made some mistake. Therefore, what is our eigenspace in this case? So it is minus 2t, y is 0, and z is again minus 2t, such that this t belongs to what? R. So which is further equal to, take this t out, so what will you left out inside? Minus 2, 0 and minus 2, such that t belongs to what? R. So we got the basis of the eigenspace. So what is the basis of the eigenspace? Therefore the set is 1, 2, 0, minus 2 is a basis, okay, is a basis of E of 1. Now, and what is our eigenvector? And in the next line I will write down and, okay, and this 2, 0, minus 2 is an eigenvector corresponding to eigenvalue, is an eigenvector corresponding to eigenvalue, corresponding to eigenvalue 1. Now just note one thing, in MCQs they may ask you which of the following is an eigenvector corresponding to eigenvalue 1. So keep it in mind. Suppose this option is not there, 2, 0, minus 2, don't write that all the options are wrong. So somewhere in some option you may have scalar multiple of this also. अशी पण वेक्टर काही ऑप्शन्स मध्ये असू शकते, पण याची स्केलर मल्टिपल पण असू शकते. रिमेंबर, द स्केलर मल्टिपल ऑफ आयगन वेक्टर इज ऑल्सो आयगन वेक्टर. त्यामुळे असा जर ऑप्शन असेल 1, 0, minus 1, स्टिल इट इज राईट. डोंट से दॅट इट इज रॉंग ऑप्शन, because after multiplying this vector by half you are getting this. So it may be like this also. So if you multiply this by 3, then you will get 3, 0, minus 3. So this is also your eigenvector, okay, corresponding to eigenvalue 1. So remember, scalar multiple of this is going to be an eigenvector. So your option may contain scalar multiple and not the original one you got, but you should be very careful, okay, while dealing with the MCQs of the eigenvector. Now we will go for what? For lambda is equal to 2. Okay, now I will put lambda is equal to 2 in star. So over here I have written the star simply for simplicity. So what you are going to get, if you put lambda is equal to 2, I will get 4 minus 2 minus 3, 2. So 4 minus 3 will be 1. No, sorry, you are putting 2, right? So 2 minus 3 will be minus 1, minus 2, 4, minus 2, and 2 minus 5 is minus 3. And outside you will have x, y, z, which is equal to 0, 0, and 0. So again I will think of first row and second row only. Now see here, you cannot choose first row and third row because the first row and third row is exactly identical. So either you can go for first row, second row, or second row, third row. Most of the times first row and second row works, okay. So I will say by Cramer's rule over here, by Cramer's rule. So what you are going to get, x upon determinant of, so minus 2, minus 3, minus 1, minus 2, which is equal to minus y upon determinant of, so 4, minus 3, 2, minus 2, which is equal to z upon determinant of 4, minus 2, 2, minus 1, which is equal to t, where this t is some parameter, okay. So therefore what you are going to get, x upon determinant of, so it will be 4 minus 3, am I right? So 1, which is equal to minus y upon, so it will be minus 8 plus 6, isn't it? So 6 minus 8 is minus 2, so it is going to be minus 2, which is equal to z upon, so it will be minus 4 and plus 4, I guess, and it is going to be 0. You will get 0 over here, which is equal to t. Therefore your x will be equal to t. Now see, this minus and minus will become plus over here, so y will be equal to 2t and z will be equal to what? 0. So that therefore what is your e of 2? So therefore my e of 2 over here is, set of all, x is t, y is 2t, z is 0, such that t belongs to R. So which is further equal to, set of all, if you take that t out, what is left out? 1, 2, 0, such that t belongs to R. So we got the eigenspace. Now what is the basis? And therefore the basis is the set 1, 2, 0 is a basis of E of 2, is a basis of E of 2. And what is the eigenvector? And 1, 2, 0 is an eigenvector, corresponding to eigenvalue 2. Now let us go for eigenvalue 3. I guess 1, 2, 3 were the eigenvalues, isn't it? Let me check it once again. Yeah, now for eigenvalue 3. Okay, so for lambda is equal to 3, I will say. So put lambda is equal to 3 in star. Now what is my star? So for simplicity, just I will paste star over here. So again I will think of first row and second row, and it is working over here also. I'll say by Cramer's rule. So x upon determinant of minus 2, minus 3, 0, minus 2, which is equal to minus y upon determinant of 5, minus 3, 2, minus 2, which is equal to z upon determinant of 5, minus 2, 2, 0, which is equal to t, where this t is some parameter. So now after solving, what we will get? Therefore x upon, so I guess it will be 4, which is equal to minus y upon, so minus 10 it will be, and plus 6, isn't it? So minus 10 plus 6 is minus 4, it will be minus 4, which is equal to z upon, it will be plus 4, I guess, which will be equal to t. Therefore x will be equal to 4t, or you can simply multiply entire thing by 4. This will also work. If you multiply by 4, because you can see that everywhere 4 is common, then also you can do multiply by 4. Okay, it is not necessary to do it, but if you do it, then it will be better. Okay, because that is what your MCQ options generally will contain. So it will be x upon 1. Now minus and minus will become plus, so it will be y upon 1, which is equal to z upon 1 will be equal to t only. It is simply the adjustment. Okay, so if you want, you can write t1 if you are getting confused, but writing t is also right. That's not an issue, because it is simply the parameter. So therefore x is equal to y is equal to z is equal to t, where this t is from R. Okay, therefore what is your E3 now? Therefore your E3 is, okay, that is your eigenspace is equal to set of all t t t, isn't it? 4 4 4 चांगलं दिसलं असतं का? नाही, चांगलं काय दिसतंय? 1 1 1, isn't it? So for better looking purpose, you can always do this adjustment such that t belongs to 1. So eigenvector 1 1 1 looks better than 4 4 4. आता मागे जे eigenvectors आपले आलेले 1 2 0 looks okay, पण त्याच्या आधी 2 0, is it 2 0? Yeah, it should be minus 2 over here, right? Minus 2 and minus 2. So instead of writing minus 2 0 2, you can go for what? Simply 1 0 1. That will also work. Okay, because you can see that over here I am having minus 2 minus 2. So if I multiply by minus 2 throughout, then I will get 1 over here, 1 over here, and I will get just simply x is equal to t, z is equal to t, and that 1 0 1 looks better than minus 2 0 minus 2, isn't it? Just keep it in mind. Okay, and find. So what is the basis? Therefore the set 1 1 1 is the basis of E of 3, and what is the eigenvector? That, and I'll say this 1 1 1 is an eigenvector corresponding to eigenvalue 3 3 3, and 1 1 1 is an eigenvector corresponding to eigenvalue 3. Now what they have asked is, they have asked us to find the eigenvalues of A inverse also. Now see, we have seen one result. If lambda is the eigenvalue of A, and suppose A is invertible, this is important, then 1 upon lambda is the eigenvalue of A inverse. 1 upon lambda is eigenvalue of A inverse. So this trick can be used. Over here, A is invertible, one can easily see. Why? Because there is one property that I think I have not told you yet. So I will write it here. Okay, just note, determinant of A is always equal to product of eigenvalues. This is very much important. Okay, and trace of A is equal to sum of eigenvalues. These two properties are very important to solve a lot of MCQs. Okay, so important properties. Always note that determinant of A is equal to product of eigenvalues, and trace of A is equal to sum of eigenvalues. You can check it yourself. So what eigenvalues I got here? 1 2 3, right? So if you calculate the determinant of this matrix, you will find that the determinant of this matrix will come out to be 6. You can check it on your own. And what is the trace of the matrix in this case? Trace means sum of the diagonal elements. So 5 plus 3 is 8, and 8 minus 2 is 6. And what is the sum of the eigenvalues? It is also 6. You can check it. 3 plus 2 5 plus 1 6. So very important properties to check whether whatever eigenvalues you got, whether they are right or not. So just note, initially whatever I explained regarding the scalar multiple of the eigenvalues, in that case I think it was 2 over here. By mistake I had written 2, but keep it in mind. Later on I understood that it should be minus 2. So in your options you may have somewhat like this option also, just for understanding. Okay, otherwise you'll say what is happening. Yeah, it was just a human error. Okay, so now yeah, now since I will write here as 1 2 3 are eigenvalues of A, also A is invertible, and A is invertible, that is required, right, for this result to be used. Therefore 1 1 upon 2 1 upon 3 are eigenvalues of A inverse. Now they have asked us basis of eigenspaces, or you can say eigenvectors also. And what are the eigenvectors? See, the result that we have proved in the last class, that 1 upon lambda is a eigenvalue of A inverse whenever lambda is eigenvalue of A. That time I have told you that the eigenvector remains the same. Means whatever eigenvectors of 1 2 3 were there, the same eigenvectors we are going to have corresponding to 1 half and 1 upon 3 also. So what was the eigenvector corresponding to eigenvalue 1? I think it was 1 0 1, isn't it? Yeah, it was 1 0 1. So minus 2 0 minus 2 is same as 1 0 1. So, and what are the corresponding eigenvectors? I'll write and 1 0 1 comma, I think 1 2 0 comma, and 1 1 1 are corresponding eigenvectors. And with the help of this you can write basis of the eigenspaces also. Okay, so that is not a issue. Now we'll go for the second one. So what is asked in the second one? So yeah, okay, so now we have to find the eigenvalues of this matrix also, and also we have to find the basis of the eigenspaces, or you can say the eigenvectors. So over here so I have to introduce some polynomial. One result we have seen, if lambda is eigenvalue of A, then f of lambda is eigenvalue of f of A, where f of x is some polynomial. Okay, So just I have to write a polynomial corresponding to this matrix. So I'll say let f of x is equal to, can you guess that polynomial? So I'll say let f of x is equal to some x cube minus 2x square plus what? This 1. Okay. So I will say as 1, 2, 3 are eigenvalues of, therefore what are the eigenvalues of f of a? Therefore f of 1, f of 2 and f of 3 are eigenvalues of f of a. Means what? That is nothing but what? So what is my f of 1? My f of 1 will be 1 minus 2. I'll write it here, 1 minus 2 plus 1. So it will be 0, I guess, isn't it? So one of the eigenvalues will be 0, 0 comma. What will be my f of 2? It will be 8 minus 2 4s are plus 1. So 8 minus 8 plus 1, I think it will be 1. And the last one will be f of 3. So f of 3 will be 27 minus 2 multiplied by 9, I guess, plus 1. So 27 minus 18 plus 1. So 27 plus 1 is 28 minus 18, I guess it should be 10. So yes, so 0, 1 and 10 are eigenvalues of f of a. You just check the calculation, okay, if I have missed something. Are eigenvalues of f of a. But what is my f of a now? Since f of x is this, what will be my f of a? A cube minus twice a square plus I. That is what we wanted. And what will be the eigenvectors? Eigenvectors will remain same as we have seen in the theorem. And I think 1, 0, 1, comma 1, 2, 0 and 1, 1, 1, I'll say are corresponding eigenvectors. Are corresponding eigenvectors. So one more is that third one, a plus 2y, I guess, and I leave it for homework. You can easily guess what should be the polynomial x plus 2. So on similar lines you can do it. So that's all for this example.